On the last week we have finished to learn mechanics, and now we are going to start learning electricity and magnetism. And especially we are going to start learning electrostatics. I think you know about electric charges. You know about electric charges from school, but now we are going to learn properties of electric charges more particularly. And the first thing, what is necessary to say? What is necessary to say that the unit for electric charge is Coulomb. Is Coulomb, and the next thing that electric charge that is assigned by Q. That is signed by Q. Electric charge is always equal to integer number of elementary charges. So every electric charge can be written as this, where E is elementary charge. So I can write that E is equal to 1 164 to 176 3 and multiplied by 10 to the power of minus 19 coulombs. Minus 19 coulombs. This is elementary charge. Elementary charge. This is elementary charge. It is one of fundamental physical constants, and n is integer number. So every charge can be written or can be considered as integer number of elementary charges. And what is necessary to say? Necessary to say that in closed system, electric charge is always a constant. So again, in the closed system, electric charge is always a constant. And this property is known as law of electric charge conservation, law of conservation of electric charge. The next property of electric charges is that there are two types of electric charges. First type is positive charges, And the second type is negative charges. And maybe you can remember that the charges with the same sign, always repel, and charges with different signs attract to each other. So two positive charges or two negative charges repel, and positive and negative charges always attract to each other. And the next question is how to define interaction between two electric charges. Uh, First experimental investigation of this question was conducted by French scientist Charles Coulomb. Um, so this name in French can be written in this way. And because of first letter in this name, we have signation Q for electric charge. So this scientist Charles Coulomb conducted investigation of electrostatic force, of electrostatic interaction. He used two charged balls. Uh, the first was fixed. And the second was connected to inconductive rod, to non-conductive rod. That was on a wire. Okay. Okay, I will write this. French scientist Charles Coulomb. This is a French spelling is quite difficult to understand. So some two charged balls. One of them is on a thread, and this charge can rotate. It can rotate. And by measuring of angle of rotation, we can define a force of electrostatic interaction between two charged balls. And based on this experiment, Charles Coulomb. Charles Coulomb defined that the modulus of electrostatic force can be calculated by formula. 1 divided by 4p epsilon 0, absolute value of Q1, Q2, first and second charges, divided by r to the power of 2. This is known as Coulomb's law. Coulomb's law of electrostatic interaction. Coulomb's law of electrostatic interaction. And what is epsilon 0? Epsilon 0 is equal to 8.85 multiplied by 10 to the power of minus 12 farads divided by meters. And this is fundamental constant. That is known as electric constant. I think I will type this electric constant. Or vacuum permittivity, or permittivity of free space, or permittivity of free space. Permittivity of free space. This is epsilon 0. This fundamental physical constant, and this is equal 8.85 multiplied by 10 to the power of minus 12. And so it is necessary to frame this with red. And I will write this here. So I see. So this is Coulomb's law. Okay, and the next question is how to write this in vector form, because this is a scalar form, and we need to write this in vector form. So let's have a look at the next picture. Let's imagine that we have 2 point charges. A point charge is a charge that have neglectable small size. So charge with infinitely small size. it can be called it can be considered as a point charge. So we have 2 point charges, Q1 and Q2, Q1 and Q2. And the radius vector of first charge is R1, and the radius vector of second charge is R2, Okay, and how can we define, in this case, how can we define vector of electrostatic force? Vector of electrostatic force, or vector of electrostatic force of electrostatic interaction between these two charges. Let's define vector R. Vector R from that is from Q1 to Q2. This vector R is equal to R2 minus R1 So how can we define a vector of electrostatic force in this case? If both charges are positive or negative, electrostatic force will be force of repelling, repel. So it will have the same direction as vector R. So if both charges are negative or both charges are positive, this force will have direction of green arrow. And this is force. This is force that is impressed on charge Q2. Force that impressed on charge Q2. That is acts from charge Q1 on Q2. That is shown by green arrow. So we can write this in the next way. That F is equal to 1 divided by 4p epsilon 0, 4p epsilon 0, 4p epsilon 0, and multiplied by Q1, Q2 divided by absolute value of vector R to the power of 3, and multiplied by vector R. And it is you can see that if we take absolute value of this force, we will obtain this. From absolute value of force of vector of electrostatic interaction. And from our picture, we can write that this is equal to 1 divided by 4p epsilon 0, Q1 and Q2 and Q2, a modulus R2 minus R1 to the power of 3 to the power of 3, and in brackets R2 minus R1 minus R1 minus R1. So this is force of electrostatic interaction. Force of electrostatic interaction. And as you can see, here we have product of charges Q1 and Q2. If one of them is positive and the second is negative, we will obtain minus. We will obtain minus here. We will obtain minus, and it means that electrostatic force will be force of attraction. Force of attraction. If one of charges is positive and the second is negative. The second is negative. The force will be force of attraction. And if both charges are positive or both of charges are negative, force will be force of repel. Will be force of repel. And this law is known as Coulomb's law. This is Coulomb's law. Coulomb's law. This is Coulomb's law for electrostatic interaction force. Electrostatic interaction force. Electrostatic interaction. And as you can remember, for gravity field, we have learned a law of universal interaction, and as you can remember from mechanics, for gravity interaction we have such formula: m1 m2 divided by r to the power of 2. And as you can see that this formula is very similar to this. So it is necessary only to make some changes, to transform one formula into other. It is necessary only to change Q with M, and to change 1 divided by 4p epsilon 0, to change this into gravity constant G. But for gravity force, we don't have modulus here. We don't have modulus here because we don't need this, because mass is always positive. And gravity force is always force of interaction. Is always force of attraction. So two masses cannot repel. They always attract to each other. But the law of gravity interaction is very similar to Coulomb's law of electrostatic interaction. Okay, and the next thing to learn, let's define the force of electrostatic interaction between point charge Q, and point charge QI, for example. In this case, we have force of electrostatic interaction Fi, and this is equal to 1 divided by 4 p epsilon 0, 4 p epsilon 0, 4 p epsilon 0, q and qi, divided by r minus ri, according to Coulomb's law, and to the power of 3, and multiplied by r minus ri. And if we have interaction between charge Q and many charges Qi, we will have many forces. And their vector sum can be written as sum of Fi, and this can be written as Q divided by 4 p epsilon 0, 4 p epsilon 0, and multiplied by sum of this, values. But it is necessary to remove Q from here. It is necessary to remove Q from here. So we obtained this. And it means that this is force. Impressed on point charge Q. Force that acts on charge Q from many charges, Q1, Q2, Q3, and etc. And from here we can obtain that force F divided by charge Q equal to this. This is equal to this. It is equal to this, but I will remove Q and write 1. And what can we say? About this relation F divided by Q? We can notice that the we can notice that right part of this formula, right part, doesn't depend on Q. It doesn't depend on Q, and it means that the left part F divided by Q doesn't depend by Q either. It doesn't depend by Q either. So we can make a conclusion. We can make a conclusion, and that F divided by Q, force impressed on charge Q divided by this charge, doesn't depend on this charge. And this value is known as electric field intensity. This is electric field intensity. This is electric field intensity. This is electric field intensity. I will frame this. I will frame this in red. And this is electric field intensity. Electric field intensity. Electric field intensity. This is electric field intensity. Electric field intensity that is produced by a system of electric charges Q1, Q2, Q3, and etc. Okay, and if we have only one charge, it will produce electric field intensity. It will produce electric field intensity that is equal to 1 divided by 4 p epsilon 0, 4 p epsilon 0, and here we have this. So electric field that produced by the point charge Qi. Point charge Qi. And from here and here, we can obtain that from here and here, we can obtain that electric field of many charges can be calculated as sum of their electric fields. So electrostatic field. It is better to write this. It is better to write this here. It is better to write that this is electrostatic field. Electrostatic. Let's fix this. It is electrostatic field because I mean field. I mean field that produced by system of fixed charges. So fixed means that they cannot change their position in space. So electrostatic field is electric field that produced by system of fixed electric charges by produced by system of charges that cannot change their place in space. And from this formula we obtain that electrostatic field of system of electric charges can be calculated as sum of electrostatic fields produced by each of these charge separately. And this formula is known as superposition principle. This is a superposition principle for electrostatic field intensity. So this is a superposition principle. Superposition principle. Superposition principle. Vector. Vector. This is superposition principle. And this is a superposition principle. Okay, do you have any questions about this? No questions. No questions. Okay. So let's consider a point charge Q. That placed in the origin. So let's consider point charge Q. That is in the beginning of wrapper system, that is in the origin. And let's calculate electrostatic field intensity in point that is defined by vector R. And how can we calculate this? How can we calculate this electrostatic field? According to the formula that is written above, we can write that electrostatic field will be equal to will be equal to 1 divided by 4 p epsilon 0 q divided by absolute value of vector R, to the power of 3, and multiplied by R. This is electrostatic field that is produced by a point charge Q. And what can we see from this formula? From this formula, we can see that electrostatic field is a central field. This is a central field. But we know from mechanics that every central field is a potential field. So electrostatic field is always a potential field. It is potential field. And what does it mean? It means that work of electrostatic force doesn't depend on the on path. It doesn't depend on path. So work of electrostatic force depends only on initial and final position. It depends only on initial and final position. So I can write for work of electrostatic force. I can write that if some charges was moved from point 1 to point 2, electrostatic field will make work A12 that is equal to minus potential energy in final position minus potential energy in initial position. Double V is potential energy. Is potential energy of charge Q in electrostatic field. I hope you can remember from mechanics that for every potential field we can define potential energy. And the same situation is for electrostatic field. For electrostatic field, we can define potential energy, and work can be calculated. Work can be calculated with this potential energy, and it can be written as minus integral from initial position to final position, from initial position to final position, F force of electrostatic interaction, dr force of electrostatic interaction. Okay, and how to define potential energy? How to define potential energy? We can remember from mechanics. We can remember from mechanics that potential energy can be defined as minus integral of R0 to R, where R0 is some origin that can be defined as we want to define. So we can choose this origin. We can choose this in initial position R0. We can choose this F dr, and plus double V 0, plus double V 0. Double V 0 is a potential energy. Potential energy is in point R0. This potential energy we can also define as we want to define. We can also define this we can also choose this. We can also choose this. In the most cases, it is chosen as equal to 0 in the most cases, but not always. Not always. So I'll leave this. And from here we can define a new physical value. New physical value that is known as electrostatic potential. Electrostatic potential. It can be defined by dividing of potential energy by electric charge. If we divide potential energy of electric charge Q, if we divide this by this charge, we will obtain electrostatic potential minus integral from R0 to R, F electrostatic force divided by charge Q, D R, and plus omega 0 divided by Q. Divided by Q. And let's make some signations. Let's write this relation as P in point R, in point with radius vector R, where phi is electrostatic potential. F divided by Q is electric field intensity. You remember this? This is electric field intensity. And this we will write as phi 0. Electrostatic potential in origin. So from here we have that phi in point R, is equal to minus integral of R0 to R electric field intensity dr, and plus phi 0. So this is electrostatic potential. Okay, so do you have any questions about this? Do you have any questions? No questions. Okay. Okay, and it is better to extend this. It is better to write here that this is potential energy of charge Q divided by this charge. So this will be definition of electrostatic potential. This will be definition of electrostatic potential. It derives from the definition of potential energy. It derives from definition of potential energy. Definition of potential energy was given in mechanics. It was given in mechanics, and now we can use this in electrostatics. Now we can use this in electrostatics. Okay, so we have electrostatic formula for electrostatic potential. Static potential. Electrostatic potential. And it is necessary to say that electrostatic potential can be defined only for electrostatic field, only for potential field. It can be defined, but not electric field. Not every electric field is potential. For example, electric field that is produced by changeable magnetic field is not potential. But electrostatic field that is a field that was produced by fixed electric charges is always potential. Electrostatic field is always potential, and electrostatic potential can be defined in this case. Okay, and let's use this definition. Let's use this definition here. From here we can write that work on path from point 1 to point 2 divided by charge q is equal to a minus potential energy 2 divided by charge q minus divided by charge q, and this will be minus integral from R1 to R2 F divided by Q dr F divided by Q dr. And from this definition we can write that this is potential in point with radius vector R2, and this is electrostatic potential in point divided by radius vector R R1, and F divided by Q is electrostatic field intensity. Is electrostatic field intensity. So work of electrostatic forces, of electrostatic interaction is can be calculated from here. Can be calculated by this formula. Can be calculated by this formula. Minus Q phi in point R2 minus phi in point R1 in point R1, and this is equal to minus Q integral from R1 to R2 E electric field intensity dr. So this is work of forces of electrostatic interaction. Work of forces of electrostatic interaction. Electrostatic interaction can be calculated in this way. It can be calculated in this way. I think I will write this somewhere here. Work of forces of electrostatic interaction. It is important that this work depends only on final and initial positions and doesn't depend on path. On path of transition from initial to final position. It doesn't depend on path. It depends only. It depends only on initial and final position. Okay, and from here and from superposition principle for electric field intensity, we can obtain from here, and from here, we have that phi, electrostatic potential of system of electric charges, is equal to sum of electrostatic potential. So we can generalize this superposition principle, and we can also write this for electrostatic potential. Can also write this for electrostatic potential. And so we have a very similar formula for electric field intensity and electrostatic potential. But it is important to notice that for electric field intensity we have vectors, and electrostatic potential is a scalar value. This is scalar value. It is important to know. Okay, and let's try to calculate. Electrostatic potential for point charge. So here we have electric field intensity for point charge that is placed in the origin. And let's try to define electrostatic potential. Let's try to define electrostatic potential for point charge. electrostatic potential for point charge. We can use this. We can use this from the definition of electrostatic potential. And let's try to do this. And let's choose some initial position as infinity. So infinitely distanced point. This we'll choose as infinity, and phi 0, we will choose as 0. We will choose as 0. And let's try to calculate electrostatic potential for electrostatic potential of positive point charge Q. Positive point charge Q. This will be according to the definition. According to the definition, it will be minus integral from R0 to R E. Oh, sorry, not R0. I will take into account. I will take into account that we have infinity here. From infinity to R, d dr. And so here was taken into account. Our choice that R0 is R0 tends to infinity, and phi 0 is equal to 0. It was our choice. And from here we have that it will be integral from R to infinity. From R to infinity, electric field intensity dr. And as you can remember, we can always choose. We can choose way from R to infinity because electrostatic field is potential field. It doesn't depend on way from R to infinity, so we can choose this way. And let's choose this way. Let's choose this way according to the condition. According to the condition that dr has the same direction as electric field intensity. So we have chosen a way of integration according to this condition. This double arrow means that the direction of E and dr are the same. And according to this, we have that this scalar product, is equal to E dr e dr multiplied by cosine of 0. Why 0? Because the direction of vector e and dr, the directions of e and dr are the same. Directions are the same, and it means that angle between vectors is 0 degrees. And the cosine of 0 is equal to 1. So we can rewrite this in this way. So from here we obtain that it will be integral. It will be integral from from r to infinity e dr. So it is almost the same integral, but it doesn't contain any vectors. This integral is much simpler than linear integral that was before. And what is e? What is e? E is modulus. E is a modulus of electric field intensity. Modulus of electric field intensity. And it will be from here. It will be this. And because of positive value of charge q, we can write that this will be 4p epsilon 0, 4p epsilon 0, q, charge q, divided by 4, divided by r to the power of 2. 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 And so we have, it means that we have here in our integral, we have 1 divided by 4p epsilon 0, 4p epsilon 0, 4p epsilon 0. Here we have q. Here we have q. Integral from r to infinity. From r to infinity. From r to infinity. And here d r divided by r to the power of 2. And how to calculate this integral? I hope you can remember from calculus or mathematical analysis that this is so-called improper integral, and it can be written. It can be written with limit 4p epsilon 0, limit alpha tends to 0. Alpha tends to 0. And here we have integral. Here we have integral that is very similar to this, but with alpha instead of infinity. With alpha instead of infinity. And we can calculate this integral. We can calculate this integral. It will be equal to minus. It will be equal to minus. It will be equal to minus q divided by 4p epsilon 0. 4p epsilon 0. And here we have 1 divided by r. 1 divided by r from r with this sign above this. R is equal to r, and r is equal to alpha. And we will have here 1 divided by alpha minus 1 divided by r. So I have made a mistake. I have written alpha tends to 0, but it tends to infinity, of course. Of course, infinity because I have changed infinity into alpha. So it is necessary to write infinity instead of 0. And if alpha tends to infinity, 1 divided by alpha tends to 0, because 1 divided to infinity is 0. This is 0, and I have forgotten to write minus in front of this. So from here we have obtained 1 divided by 4p epsilon 0, 4p epsilon 0, 4p epsilon 0, charge q divided by r. It is electrostatic potential for point charge, for positive point charge q. In very similar way, it can be proved. It can be proved that for negative charges, formula will be the same. Okay, do you have any questions? Do you have any questions about this? No questions. No questions. Okay. Okay. So let's continue. Let's continue. It is necessary to clean some unnecessary things from here. It is necessary to clean some things from here. So we have obtained electrostatic potential for point charge. And we will use this formula in future. Phi is equal to this. So we have electric field intensity and electrostatic potential for point charge. If it is necessary to remember that we have chosen R0 tends to infinity and phi 0 is equal to 0, and phi 0 is equal to 0. It is necessary to remember this. So this is electric field intensity. Electrostatic. I will write electrostatic field intensity. Electrostatic field intensity and electrostatic potential for point charge Q. For point charge Q. For point charge Q. Okay, and do you have any questions about this? No questions. No questions. Okay, if there are no questions, let's do the next things. Here we have formula that allows to calculate electrostatic potential from electric field intensity. And let's solve another problem. How to calculate electrostatic field intensity from electrostatic potential. We can do this as we remember from mechanics. As we can remember from mechanics, potential that force of potential field can be calculated by this formula minus gradient of potential energy. It is from mechanics. And let's divide left and right parts of this formula by charge Q minus gradient of potential energy divided by U. And as you can remember, potential energy divided by charge Q is electrostatic potential phi, and electrostatic force divided by charge Q is electrostatic field intensity. So this will be E. So from here we have that electric field intensity electric field intensity, electrostatic field intensity is equal to minus gradient of potential phi, minus gradient of potential phi. And I'll remind that this vector differential operator is equal to minus d by dx e, not minus, sorry, it is plus, of course it will be plus, plus d by d y yacht, and plus d by dz k. This is a connection between electrostatic field intensity and electrostatic potential. And electrostatic potential. And electrostatic potential. And electrostatic potential. Oh, and it can be proved. It can be proved that using this formula, we can obtain this from this. We can obtain electrostatic field intensity of point charge Q from electrostatic potential of this point charge. Okay, so do you have any questions? Do you have any questions? No questions. No questions. And the last thing for today is electric flux. I will write only a definition. That electric flux. Electric flux. This is F E, big Greek letter F E, and it is equal to surface integral of E ds. Surface integral of E ds. This is electric flux. Electric flux. Okay, do you have any questions about this? Okay, if there are no questions, thank you for your attention, and I hope to meet you next week.